Good afternoon to you, buon après-midi a vous, buon pomeriggio a tutti voi. Welcome to Paris and to the International School of Astrophysics Daniel Chalonge, Hector de Vega, for this special session in the honor of Adam RIESS, professor at Johns Hopkins University, who is awarded Nobel Prize of Physics, and who is awarded today of the Daniel Chalonge Medal and Hector de Vega Medal of this year. And we proceed, as you can see from the program, we are proceeding with this. And after the presentation of this short introduction, Adam RIESS, as announced, will present his lecture, his conference on the Hubble constant and all the recent results. Then after the question session and discussions, and this after, in the tradition of the school, the congratulation and the true French champagne. And Adam RIESS, Bloomberg Distinguished Professor at Johns Hopkins University and Nobel Prize of Physics, received the medal Daniel Chalonge and Hector de Vega this year for his contribution to his discovery of the acceleration of the present acceleration of the universe and dark energy, in the interpretation of this as a cosmological constant, and for his particular the medal for his continuous results on the Hubble constant, which is the center, which is a central problem of cosmology today and fully in the cosmological actuality. As you know, the pandemic period enabled to do this presentation to do this session in physically, but have not enabled to present the Chalonge and Hector de Vega medals to Adam already. Adam got the medal physically. This is not just only a virtual medals. And as you can see here, in the Adam is well placed there to see the amplitude of the pandemic and the advances are going on for that. But you see from the Johns Hopkins announcement that the medals, the two medals and the document of the award are in his place. This is not a picture just made in Paris. This is a picture where the medals now of Adam are, and from his place in Baltimore, Maryland. Adam, if you allow me some 20 minutes, say, I will make a short history of these medals, rich history of the medals. The present, the previous Chalonge award of the medal started distinguished scientist, and started with the first presentation in 91 to Chandra, a Nobel Prize of Physics, and great friend of Daniel Chalonge, who came to the first course, inaugurated the first course of the school in Italy, in the Majorana Center, Ettore Majorana Center, and delivering his lecture on Daniel Chalonge and the problem of the abundance of the hydrogen, because at the time the abundance of the hydrogen was at the center of a scientific debate. It was not so trivial and clear as it's not today. And Daniel Chalonge provided measurements on the negative ion of the hydrogen, which Chandrasekhar, who was studying the problem theoretically, greatly appreciated and recognized it. And Chalonge made that with his collaborator with his own instruments, spectrograph and microphotometer, which allowed to reach him the far ultraviolet, and in the observations in the stellar atmospheres. Then after it was because it was possible to do that because at the time Mrs. Chalonge offered me the three last medals she conserved, and one I gave Chandra in recognition, acknowledgement, because he was aged, and despite of his age came from Chicago to the south of Italy with his wife Letitia. And one of the medals I gave to him, one was I placed it in the Chalonge Museum I created with a school in Italy. And the third one was the 92. I offered to Bruno Pontecorvo, pioneering in neutrino physics, neutrino oscillations, who coined the name sterile neutrinos, and great participants of the school from the beginning, and who offered me draft and his draft of the computations, part of his original articles, which are I placed in the Dirac Museum I associated and created in 92, associated to the Chalonge Museum, because it was all the saga of particle physics and astrophysics at that time, which was high energy, which was cosmic rays. And then after, till 2006, there were no more medals, no more awards. And it was the Nobel Prize, it came the Nobel Prize of Physics to the COVID team for the discovery of the anisotropy of the microwave background radiation. And then I wanted to recognize the assiduity of the lectures by this team, in particular George and also Sean Matter. But at that time we organized the Paris Nobel Conference in December 2006, devoted to this subject, in which, in a totally surprise award, I offered to George Smoot the Chalonge medal. It was possible because In a great action of generosity, the designer and the sculptor of the medal, who was a lady, Madeleine Pierre Querol, aged the age of 90, more than 90, 93 at the time, always active in her Parisian atelier, workshop, and she offered me her own medal. There were no more medals, Chalonge medals, and then which I offered to George. And then in also extraordinary action, the French mint, who coined the money, la Maison de la Monnaie de Paris, which coined the medal, accepted to perform a second edition of the medal, because we have the archives, we have the molders, they conserved and this allowed to identify and provided in the traditional way they do the second edition of the medal exclusively for the school, which allowed to continue with these awards. And then in 2008, Anthony Lasenby, pioneering the cosmic microwave observations also in Europe and from the ground, because and Bernard Sadoulet, pioneering astroparticle physics and direct particle, dark matter detection, proposing experiments for that, because one of the key words of the school is pioneering, and the award encompasses that. And then Peter Biermann, the year after, for pioneering working high energy astrophysics, cosmic rays, AGN, and interstellar medium. And then after Sean Matter, Nobel Prize of Physics, who came many years from the beginning also of the school, and for his exquisite measurements of the CMB spectrum of the, and then Brian Schmidt, Brian, who was also in the school lecturing before the Nobel Prize many years, several years, because of this present acceleration, which was not accepted by many teams or many colleagues or teams. It was said that they were just systematic effects or other effects, etc., etc. But we always in the school from the beginning interpreted and followed such interpretation, such discovery as Brian presented, and Brian result the team found, and which achieved for them for the Nobel Prize, precisely shared with Adam RIESS, Adam here, and Saul Perlmutter from Berkeley. And then after Gerard Gilmore for pioneering Gaia mission, Gaia in Europe. And then after 2015, Hector de Vega, theoretical physicist who had several scientific lives from pure physics, quantum field theory, and integrable models, and then inflation, then astrophysics, dark matter, and cosmology included also dark energy. Nicholas Kaiser, Nick Kaiser, Golden Medal of the UK Royal Society, also for pioneering gravitational lensing, who is here too. I acknowledge his presence, as the presence of George Smoot, as the presence of Peter Bierman and others, and Anthony Lasenby here. So we are accompanied by several awarded of this medal. I thank very much. And Adam, Nobel Prize of Physics, who shared with Brian, and we, as I said, with Permuter, and who is our distinguished guest today. The medals are the Chalonge medal, for those who do not know, and is the portrait of Daniel Chalonge made by Madeleine Pierre-Querol, who is a noted also a painter from Matisse, the cabin in the workshop of Matisse in the south of France, and then came to Paris, and also medals of personalities and writers and antique personalities, and as this reverse side of the medal is depicts two ascent. The upper half is the mirror of a telescope on which the French, the Milky Way and the Orion constellation observed by Daniel Chalonge are shown, and the lower half are the French Alps and the point or the peak, so-called peak Chalonge of 3,343 meters, because Daniel Chalonge was also a passionate of climbing, and with his instruments he came, across Europe, the mountains, and in particular to Italy, and in particular to the Swiss, in which there was, and still there is, the Jungfrau Joch scientific station, and where he arrived with his spectrograph or microphotometer, and scientists from Europe of different disciplines, particular physicists, came, and particularly the astroparticle physics at that time, the cosmic rays, and they he met great friends of Laquette, Auger, and other people, Joliot-Curie and others, and they are the grounds, the discussions for the creation of a European organization for that, which was the CERN. The creation of CERN in Geneva came from that. And Madeleine Pierre-Querol, who died at the age of 100. Till the end, she was always active. And the Hector de Vega medal was coined by the Maison, a traditional known Maison Canal, the medalist, traditional medalist, under a magnificent sculpture, the portrait, under the photograph made, the last photograph of Hector made by Nadia Charvite Blumenfeld, who was a great friend of us, of the school, from the known Blumenfeld family. Blumenfeld from Berlin, Paris, Princeton, and Cambridge. Nadia, daughter of Kathleen and Henri Blumenfeld. Kathleen, photograph, very well known of personalities, presidents, saints, queens, and Henri, daughter of Henri Blumenfeld, who is a physicist in the Saclay Commissariat de l'Énergie Atomique, now retired, and son, Henri, son of Erwin of the photograph. I mean, also pioneering self-made genius, Erwin Blumenfeld, who came with the group of Dadaism, and in Paris with Man Ray, and who made pioneering plates in capturing light in the way during photograph, and was a very, I mean, then after very well known in United States in the Vogue, one of his activities to live in Vogue, and there are now museums, and these were among them Elaine from Cambridge, UK, great friends of the Dirac Wigner family, when Dirac was in Cambridge, very near from Blumenfeld family. And then when he came to Florida, Tallahassee University as a professor there, Elaine performed the sculpture of Dirac, which is placed in the memorial in the Dirac Library of the University of Florida at Tallahassee. And here you can see all the people. I mean, we mention some of them and many others as in the school, which is aimed to be really as a laboratory of ideas, and which has been, and it is, we consider a great scientific and human adventure. And many of the participants in this session, virtual session, are here in these pictures, and including, I mean, at the time, including the astronauts too. As several astronauts came to the school from the international space station, and some of them pioneering. And it's a totally surprise award, as we have said, and we next year we hope it will be more surprise award in the tradition. And the ancestor is occasion also to show to you this is historic, recent, I mean, in some sense, it's 1986, the ancestor of the school, this colloquium which we put it together. You see Stephen and many others, very well-known theoretician and physicist in gravity, together with Stephen and the Cambridge and many other places, because at the time was precisely a so-called theory of everything, string theory, which came, 2 years ago, 48, as a renewal of the old string theory of hadrons. Of course, as a theory of unification, but attempted to be a theory of unification, but was from a particle physics point of view, because as we pointed out at the time, and the colloquium is a proof of that, there was a theory of everything, but which didn't include cosmology and didn't include the black holes neither. Included the graviton, which is already a huge, at the time, a huge advance, but were not providing connection with strong gravity and cosmology and black hole, as I have said, and provided and they were not connection at the time among the specialists in that, and so we did this pioneering colloquium from string theory, quantum gravity, quantum cosmology, and in connection with that, at the time, integrable and conformal invariance theories, which we organized with Hector, and that is the reason why you see here many theoreticians from all those topics, and the gravitational specialist as Stephen, of course, Desser, Gary Gibbons from Cambridge, also, Don Page, and then Chris Pope, and all Cambridge people, and postdocs as Bernard Wartin, for instance, and now leaders in the LIGO, or Bruce Allen from US, and now were postdoc leaders in the LIGO collaboration for gravitational waves. And so were others, as David Olive for the theory, strings and conformal field theory, Paolo Di Vecchia, Rittenberg, Hogel-Nielsen, Corrigan, and well, I cannot mention all Ramph, Curright, and well, I will stop to mention was Eichelburg also for general relativity in Vienna, and was also not in the picture out of the field François Englert, not at the time Nobel Prize, but got the Nobel Prize from the with Peter Higgs in 2013 for the Higgs. He did the mechanism for the Higgs with Brute, and several others. So you can see more, the inauguration, Pontecorvo, Mrs. Divan, which is living one of the only collaborators with Querelle, which were there, Roger Querelle, and the Chalonge students said were there, and Haladnikov, George, Chandrasekhar and Letitia Chandrasekhar, Michael Turner out of the field, Fang Li, and Weber, and many others which are students and now becomes lecturers, and Hector and Tom Keeble, which was from the beginning in the school. and several others. And then the second, in the second, you can see for Fishman, for the gamma rays bars, Schraman, every Shasman was also, and Israel Pontecorvo, always there, Halat, Lasenby, Smoot, Lindenbell, Craig Hogarth, and Peter Berman and his wife, the last postdoc in Princeton, the last postdoc of Einstein. He formulated one of the, also pioneering the formulation using the formalism of Dirac, but in general relativity, one of the formulations of the Hamiltonian or canonical, so-called canonical formulation of general relativity. Parisky and Blumenfeld, well, Shapiro, of course, for cosmic rays, and many participants. And this is in the meridian of Paris. You see in 2011 or 10, and many people, I mean, Alba always there. So you can see that was a continuous activity. And in 2013, in July, this also on the meridian of Paris, the 3 Nobel Prizes in modern cosmology and several Chalonge, 6 Chalonge medals meted there in this colloquium. Extraordinary meetings and fond memories. And you see that the school came, and the medals came with all this legacy. The medals are given with all this legacy of the school. And recipients of the Daniel Chalonge Medal and Hector de Vega Medal are ambassadors of the school, with science with great intellectual endeavor and a human face. Students become lecturers, lecturers become Nobel Prizes. The impossible in science yesterday, which was thought impossible in science yesterday, became a standard, or so-called standard today. And this is what we mean by a great scientific and human adventure. So we see here the Cité Internationale Université de Paris, the international city of the University of Paris, in a very pleasant and green place, in the quarter near the Paris Observatory, which is very appropriated in it's a peace garden, I said, and Jardin de Paix. You see here is very appropriated campus for scientific creativity and very peaceful. Where we in the recent years we do the meetings, and where was planned to do the meeting for, and all the reservations and so on of the facilities. But we hope to do in the next year. And with that, I thank again Adam. We are very pleased and very honored to have Adam today to receive the medals, and he got already the medal. So now I stop to share my screen and announce and call Adam for his conference. Thank you very much. And please, Adam, now is yours.
So I joked about running a tape measure out to a star, but in essence, that's what you would like to do. But we knew that do the next best thing, for example, measuring parallaxes of those stars. And this is done at distances of kiloparsecs, or later I'll describe megaparsecs. This is what we call the anchor step, okay? Step 2 is to look at nearby galaxies that already hosted type 1a supernovae and go back with the Hubble Space Telescope and observe Cepheid variables in those galaxies, using one to calibrate the other. So this is the cross-calibration step. This is usually done at distances of 10 to 40 megaparsecs. One thing that often confuses people, so I'll just point this out, the key assumption here, which is hardly an assumption, is that the Cepheids and supernovae, by being in the same galaxy, are the same distance from us. The distance between the Cepheid and supernovae is inconsequential. It's really the distance to the combination that we measure. And then finally, type 1a supernovae out into the Hubble flow, where their redshifts are compared to the distances inferred and to determine the Hubble constant. So a couple of important reminders. There is no astrophysical modeling here. We are not running models, stellar evolution models. This is completely empirical. It is based simply on the Cepheids here being the same kind as the Cepheids here, or the type 1a supernovae here being the same as the ones here. There is no use of general relativity, or virtually none, and there's really no use of the cosmological model. I say virtually none because we're not doing this all at 0 redshift, but very, very small redshifts of more like 0.04. So the sensitivity to those things is exceedingly small. However, the most important aspect of this measurement, to make it precise, is to maintain consistency between the measurements done here and here and here and here. So I'm going to talk about the extreme efforts we've gone through to try to maintain that consistency. Okay, so let me talk about the first step, measuring distances to Cepheids with parallax. This is harder than it might sound, simply because most Cepheid variables are kiloparsecs away, which means the parallax angles become fractions of a milli-arc second. Or in other words, if you wanted to observe a star move back and forth over the course of a year, a Cepheid, because you were trying to measure its parallax, that motion that you would see, the motion, of course, that's due to the Earth going around the sun and our perspective on that, that motion or parallax angle you're trying to measure would be just a few hundredths of a pixel on the Hubble Space Telescope's most highest resolution camera. So that's not an easy thing to measure. However, we had a cute idea a few years ago of how to do just that, how to make a better measurement. See, the limitation is really measuring the relative separation of two stars when the precision of centroiding a star is about 100th of a pixel, which would be like a 1 sigma measurement of a typical Cepheid variable. So we realized we could spatially scan or move the telescope during the observations to repeat the measurements over and over and really beat down the errors in the ability to centroid a star. And so if you're confused what I'm talking about, we literally moved the telescope during, during the observations. Stars go flying by and they become lines, and we can compare pixel by pixel the separation. So here's a tiny patch of one of these images where you can see lots of these individual scan lines. We then go in and we extract each star's scan line pixel by pixel. We line them up in time. The first thing you notice is that there's a kind of a coherent noise that you see between different stars with them moving in the direction perpendicular to the scan. But you quickly realize this is just due to the jitter of the telescope. The telescope is bouncing along in the direction perpendicular to the scan. That's okay. We don't care about that. We only care about measuring the separation between stars. So when we subtract two of these lines, the jitter goes away. This is even better than imaging because we are actually resolving, sampling, and removing the jitter. And then we get to beat down the errors. And so with this technique, we found we could get to a precisions of 20 to 40 micro arc seconds. These are useful numbers to keep in mind as I talk about Gaia in a few minutes. And so over the course of 4 years, we used this technique to observe about 8 Milky Way Cepheids. The W's, or back and forth motion you see here, is the parallax of these. So the inverse of that tells you the distance. Having measured 8 of these, we were able to calibrate the luminosity of the Cepheids geometrically to about 3%. Meanwhile, the European Space Agency is flying this spectacular mission, Gaia, to measure parallaxes of all the stars in the Milky Way. And round by round, it is improving. We anticipated that the best combination of all would be the parallax measurements from Gaia, but still the photometry or brightness measurements of those Milky Way Cepheids from Hubble, so that you can combine those and use them to compare to the distant Cepheids, which are only observed with Hubble. And so therefore we picked 50, what I would call benchmark Milky Way Cepheids, observed them photometrically with Hubble, and combined their parallax measurements from Gaia as they came out 2 years ago in what was called Data Release 2. These parallaxes were not the best ones that Gaia can do, and so the precision was limited to about 3% overall. However, what's so exciting about giving this talk today is Gaia Data Release 3 just came out just 3 hours ago. And I've already been able to take a quick look at it, and I'm very excited about the improved data quality. It looks very clear to me, at least, that we should be able to get to a better, at least 1%, if not better than 1% calibration with the new higher quality Gaia data. So stay tuned for that. Already, though, with the past parallax measurements done 3 different ways, has been enough to calibrate the absolute period luminosity relation of Cepheids, particularly at the longer periods, where those are the only kinds of Cepheids you can see in type 1a supernova hosts. And also by photometrically observing these with the Hubble Space Telescope, they're on the same photometric system as the ones in the supernova hosts. And so I just said that Gaia Data Release 3 should support a 1% calibration of the Hubble constant. Gaia Data Release 4, or maybe I should just say the final Gaia Data Release, according to the specifications and expectations, should really support a 0.4% calibration of the Hubble constant. So these are very exciting times in my mind to be trying to make these measurements. Okay, parallaxes are not the only way to geometrically calibrate the luminosity of Cepheids. Another powerful way is to measure geometrically the distance to stars in the Large Magellanic Clouds, stars that are in detached eclipsing binary systems, where observations of the orbit tell you the physical size of the star, and a relation calibrated through interferometry tells you the angular size of the star, and comparing the two gives you the geometric size. This has been done to 1.2% most recently. And a third way that I like quite a lot, which is observations of water clouds, masers, in the radio orbiting a supermassive black hole in a specific galaxy, NGC 4258, has been tracked through 10 years of Keplerian motion and gives a 1.5% geometric calibration there. So these are all quite independent, which is a very good thing when you're trying to measure a number very precisely. Okay, step 2, and this is really the rate limiting step for precision, is to be able to observe Cepheids in the hosts of recent type 1a supernovae. A single type 1a supernova measured distances that are good to about 6%. So you're never going to do much better than 6% over the square root of the number of those supernovae. And there's a very limited distance range to which you can measure Cepheid variables. Nature produces a type 1a supernova in that volume, a volume of about 40 megaparsecs in radius, about once every year or two. And so by calibrating just the best type 1a supernovae and the requirement that the host is within a redshift of 0.01 so we can reach its Cepheids, by the end of this year, we will have completed the sample, a complete sample of all type 1a, all such type 1a supernovae. That'll bring us to about a total of 38, maybe 40. And that's probably about the best we can do without, waiting decades more for Hubble or nature, to produce more type 1a supernovae. Okay, the next step is, of course, to measure the period luminosity relationship for the Cepheids in the galaxies that host the type 1a supernovae. That's been done recently for 19, and we're very close to doubling that now. And of course, in these anchor galaxies that I talked about as well. Now, here's the part I wanted to really focus on and help you understand why these measurements have such low systematics. And that is because for the first time, we are making purely differential flux measurements. We are observing Cepheid variables in these geometric anchors and in the type 1a supernova hosts using the same instrument and the same filters and the same types of Cepheids over the same period range. So it really is just a differential measurement. Knowledge of the absolute 0 point of the telescope drops out of the analysis. Here are stacks of the light curves of the Cepheid variables in each of these galaxies so you can appreciate how similar these objects really are. And another way we've been able to reduce systematics over past measurements has been by making those measurements in the near infrared. Past measurements were generally done in the optical, but most distance indicators, most standard candles are better distance indicators in the near infrared because you can see through the dust more easily. And this is illustrated here in the Cepheids in the Large Magellanic Cloud, first discovered by Henrietta Leavitt 100 years ago. As you go from the optical down here to the near infrared, you see the relationship gets tighter and tighter as the differential dust becomes more and more insignificant. And also differences due to chemical abundance become much smaller there. Most of the lines are actually in the optical. And so working in the near infrared is a big advantage to reduce systematics. And then the third step, of course, is, as I described before, the fact that type 1a supernovae measure the expansion of the universe. And so we determine that. We account for small changes in the expansion rate, but these are pretty trivial. And what we're essentially doing is measuring what is the characteristic brightness of a Cepheid at a given redshift so that we can calibrate it with the preceding two steps. And so this is all done simultaneously in what I would call a multilinear regression. We use the measurements as they are raw on the left-hand side, the Cepheids in the supernova hosts, in the anchor, the type 1a supernovae, and the geometric distance priors, then with a regression matrix that describes the relationship and the parameters, which are really just the relative distances, the slope of the period luminosity relationship. We do a simultaneous analysis with an error matrix that has covariance in it between measurements, and we determine two numbers ultimately, the absolute luminosity of a fiducial type 1a supernova and the intercept of the Hubble diagram, which go into determining the Hubble constant. So it's really three steps where geometry calibrates Cepheids, where Cepheids calibrates type 1a supernovae, and where supernovae calibrate the expansion rate. This has been done 5 different ways. This has been done so far 19 places, and there are some 300 of those. And so the answer we get most recently, or as of last year, was 73.5 plus or minus 1.4, so a 1.9% measurement in all. Now, if you remember from earlier in this talk, the Planck value was more like 67. There's quite a bit of tension here. There's about a 4.2 sigma difference from that. And so anytime you see a difference, of course, you want to look back and try to understand, is it showing up in a particular place in the measurements? So I'm going to go over that right now. But just to remind you, this is a direct measurement. The value I'm comparing to is the cosmic microwave background combined with a prediction from the cosmological model. So the first step to look at is literally the first step, the anchor step. This used to be the hardest step in measuring the Hubble constant. This has now become about the most mature step because of so much good work in this area. So we can break out now the 5 different ways we've used, and even 2 new ones that were done recently by another group, Luisa Bruval and Pierre Kervala. So using the Mazars in 4258 or the detached eclipsing binaries, or 3 different flavors, 3 different ways of measuring parallaxes. The older ones done with Hipparcos or the Hubble Space Telescope's fine guidance sensor, the ones with our new Hubble Space Telescope technique of spatial scanning, or Gaia data release 2. These all give very consistent results in the low 70s. A more recent effort was made using Gaia data release 2, but not the Cepheids, rather their companions, either their binary companion or the cluster in which they live. It's a very clever way to really find, make sure you don't have the same systematics as other methods. So all of these methods would have very different systematics, and yet to within 2 sigma, give very consistent results. So there's really, I would say, no relief coming to this, this tension from the geometric calibration. But that's okay. Let's move on to other kinds of variants of the analysis. Just to keep in mind the difference between what we see and what Planck plus lambda CDM predicts would be about 2/10 of a magnitude in one of these steps. So pretty big. This is, 2/10 of a magnitude is a pretty large difference, I would say. So we came up with 23 variants of our basic analysis, changing reddening laws, changing how you reject outliers. Normally about 2% of Cepheids are outliers. How you truncate the period range. Do you use the full range, a narrower range? Whether you fit the period luminosity relationship as a single slope or as 2 slopes with a possible break. Whether you include metallicity as a possible free parameter. Again, this is all empirical. There's no theory here. These are just choices of whether to include a parameter or not in the solution, and what range over which to consider data. Whether you start the Hubble flow for supernovae at 0.01 or the more conventional 0.02, which light curve fader you use, what kinds of host galaxies you allow the supernovae to be in. All of these things make a small difference. None of them makes a significant, or I would say important difference relative to what we have seen. Other questions I am frequently asked that I thought I would just assume maybe on your mind to answer. Could we live in a giant void so that our expansion rate is greater than the cosmic one? This would have to be about representing about 9% shift in the Hubble constant. And I guess I would say the answer is no. Large-scale structure theory predicts variations due to our local volume of about 0.6% in the Hubble constant. This is confirmed empirically by extending the Hubble diagram of type 1a supernovae and looking for a massive inflection that would belie us living in a void, and that is not seen either. In fact, it's quite consistent with the large-scale structure prediction of fluctuations at the 0.6% level. So this would represent like a 15 sigma fluctuation. Is the flux scale of the Hubble Space Telescope calibrated linearly enough to measure a 1% value of the Hubble constant, or even 2%? Yes, most recently it's actually been calibrated across 15 astronomical magnitudes to about 0.3%, and so this should not be an issue. Could the crowding of Cepheids, the fact that they live in fairly dense environments, compromise their accuracy somehow? Well, we already account for crowding using artificial injected stars. However, a powerful test of whether this is right is to look at the amplitudes of the light curves, where crowding would suppress the amplitudes. And this has been done recently to rule out that there is any significant differences from the amount of crowding or backgrounds that you expect. So there's no relief there. Could there be a difference in the type 1a supernovae at the 2 ends of the distance ladder? We look for correlations of the Hubble residuals with every other property we can think of the host galaxies. We also limit our analyses to only the same types of host galaxies at both ends. So variations here are at the 0.3%, nowhere near where you need to be. Most recently, as we sort of get, I would almost say, desperate to find a way out, I've been asked, could it be that the physics of the Cepheids, that the Cepheids themselves are different in our local part of the universe where we calibrate them? And that would mean the Milky Way or the Large Magellanic Cloud or NGC 4258. These are galaxies within 10 megaparsecs of us, versus a little more distant ones where we calibrate supernovae, maybe 40 megaparsecs. I mean, you almost want to just say this would violate the cosmological principle that, our stars and the ones in nearby galaxies around us are different than the ones just a little bit further out. Nevertheless, I was looking at this recently. There's really quite a powerful way to look at the similarity of the physics of the Cepheids, and this goes back 100 years to Hertzsprung of the Hertzsprung-Russell diagram, and it's called the Hertzsprung progression. It's the way in which it's not just the period, but the shape of the Cepheid light curves change or are correlated with period. To first order, they're very asymmetric, and this is typical of a star pulsating in the fundamental mode. But in addition, there's an additional little bump on their light curves at short periods that has been understood to result from a 2-to-1 resonance between the fundamental oscillation and a second overtone. There's a nice set of papers by Giuseppe Bono and collaborators that describe this and how that bump changes in phase. And so by stacking all of the Cepheid variables in the distant galaxies over the same period range as Milky Way ones, we can see just how similar these are. So, for example, here are all the Cepheids between periods 5 and 9 days. The black is the data point. The red is kind of the average binned version. And in blue here, the blue arrow, you can just see this little bump on the light curve. And this is very typical of, for example, in the Milky Way, this is DL Cas at period 7.6 days, right in there. And you can see how it has the same shape, and that is where this Hertzsprung bump, this 2-to-1 resonance appears between the fundamental and the second overtone. Then as you go to somewhat longer periods, that bump is known to migrate and join the primary peak of the Cepheid light curve. The same thing is seen for the distant ones as is seen in Milky Way counterparts. For example, this one at period 12.4 days. Then that bump migrates in phase to now the ascending branch of the Cepheid variable, seen here in the Milky Way Cepheid XZ car, and seen here in the compilation of all the distant Cepheids over the same period range. Then going even longer in period, here you see with RY SCO, that bump migrates to about the point of minimum of the light curve and is seen here as well in the sum of all the distant ones. Then the bump disappears and you get the classical sawtooth high amplitude Cepheid light curve seen here, RY Vel, and all the ones at those periods. The next period range, AQ Pup, very similar to the ones you see here. And then as you go to longer periods, the light curves start to flatten a little. Here is GY Sagittarius, and over that same period range, all the distant ones, and the longest period example I have here, S-Vol, and all of its counterparts in other galaxies. So the physics of the Cepheids, even in detail, looks very similar. It's very difficult to not conclude that we are looking at the same objects. Okay, so we've been tracking not just measurements, but also our error budget over about 15 years now. And each round we seem to address a different error term with a specific experiment. So the last few years has really focused on the anchors, the Milky Way parallaxes, the combination of HST and Gaia, the Large Magellanic Clouds attached eclipsing binaries with HST fluxes, improvements in 4258, better calibration of wide field camera 3. And that leaves us where we are. Now, I want to say at this point, nobody should really be surprised, I guess I would say, by the value of the Hubble constant we find. The error has come down because of the steps I've described, but it's quite consistent with what people have found for the last 20 years. Cepheids have been the most popular primary distance indicator to use because they have the longest range, so therefore you could get to the greatest distances in the most type 1a supernovae. They have the most independent ways of being calibrated because you can use direct parallax. They can be measured with in a consistent way as we have done photometrically by using the same telescope at both ends. and they're the most tested. And so I point out here 20 years worth of analyses using different HST instruments, not the same instruments we are, different teams of people, the Hubble Space Telescope Key Project, Wendy Friedman and collaborators, different people measuring photometry. Cepheids observed different wavelengths. We've had people from the Planck team reanalyze our data. We've had people use different sets of supernovae than we have used, different formal ways of doing the analysis, Bayesian hierarchical analyses instead of our sort of straightforward, multilinear regressions. And they always get answers in the same sort of range, 72 to about 75. In fact, this has become so common, it's actually a graduate student problem set problem in an astrostatistics class in Toronto. And I've looked at the solution set, and it's the same answer we get. So I guess we passed that course. Now, of course, this is not the only way to measure the Hubble constant. There are many people in the community who have really started focusing on this more and more. We had a great conference last year at KITP where people presented results based on Cepheids and type 1a supernovae, TRGB and type 1a supernovae, using Miras and type 1a supernovae, using masers directly into the Hubble flow, using Tully-Fisher, using surface brightness fluctuations, and even type 2 supernovae. We concluded at that conference in this review that the tension that you see here does not appear to depend on the use of any one method, team, or source. And this is a recent compilation from a D. Valentino. To put a more quantitative statement on this, I said our tension with the early universe, and also that's not just Planck, is at least 4 sigma. If you remove our measurements, nothing from Cepheids, you're somewhere between 4 and 5 sigma. That's why when you combine them all, it's even more than that. You can actually form combinations that are relatively independent and remove any one type of measurement if you're nervous about it, like don't use lensing or don't use type 1a supernovae. You can even say you don't use Planck or you don't use the CMB because you can use Big Bang nucleosynthesis to calibrate BAO. And the size of the tension can range anywhere from about 4 to 6 sigma. But what you don't see is, you remove one critical data set and it all goes away and becomes consistent. And so this looks, as I said, quite serious. Of course, I've been focusing mostly on the difference between Planck because that's the most precise of the early universe or indirect methods, and our own work because I think it has the most calibrations and the most precision because it has the biggest set of type 1a supernovae. So what then is causing this difference? And the truth is, I don't know, and I don't know that anybody really knows. It is tempting to think about new physics, to think of a difference that could be between the early and late universe. And so you sort of have 2 options there: change something in the late universe or change something in the early universe. Late looks quite difficult because we have high redshift supernovae and baryon acoustic oscillation data that over the later epoch of the expansion history of the universe looks very much like vanilla lambda CDM. And so that leaves you sort of pushing more towards the early universe side. And there's a good review of this recently, the Hubble Hunter's Guide by Lloyd Knox and Malaya, who described the sort of early universe route as probably the most likely. And there are various mechanisms, but they all sort of involve injecting energy more than you expected in the early universe, or having more energy there, causing the universe to expand faster before recombination, which makes it become transparent earlier. That is, recombination happens earlier. And so the sound horizon, the distance that a fluctuation can travel to that time, becomes smaller because the universe becomes transparent earlier. That changes the fundamental calibration of the CMB and of baryon acoustic oscillations. And you want to do this by about 5 to 8% in order to accomplish this. There have been various mechanisms that have been suggested to do this. An episode of early dark energy, that is a scalar field at early times, or sterile neutrinos that have, of course, have radiation-like equation of state, and so they cause it that way. However, you have to fine-tune the early dark energy or the sterile neutrinos in the form of self-interactions to avoid causing problems or inconsistencies with the tail of the cosmic microwave background, with the high L part of the spectrum. And so this is hard work right now, and that's why I don't think anybody can tell us the answer. There are other interesting clues out there. Even as recently as last week, I saw a paper claiming some evidence of cosmic birefringence from the Planck data. If that were true, that could be evidence of CMB coupling to either early dark energy or some axion-like particles. Any of those could be in play. As I said, I don't have a really good idea of what it is. Another interesting tension to keep your eye on that is not as strong as the Hubble tension, but smells a little bit like it, is in the parameter sigma 8, which measures the clumpiness of matter in the universe. Again, you can predict from Planck what its value ought to be today, and then that value comes out higher than the local measurements, which are done either from lensing or from peculiar velocities. In either case, they're about 3 sigma lower. So that seems to be interesting at the clue level, particularly from the most recent work from 6DF and Sloan. And so if one could think of a solution to this that solved both of these tensions, that would be truly exciting. So I'm getting to wrap up my talk now, and I just wanted to make some general statements at this point. And that is, people often ask me, can we really believe these measurements without having an explanation? And, it is hard, there's no question, but we've succeeded on this route many times before when we measure something long before it's understood why it's departing from our expectation. The precession of Mercury is probably the most famous, the solar neutrino problem, the missing baryon problem. And we have things today like this. We have flat rotation curves, which is, dark matter, of course, but, still waiting to really understand that. And we have the accelerating universe, and we say, it's lambda, but that still doesn't really solve the question of, why is our lambda so small? And so I think it's important when you have a measurement, even without an explanation, to sort of not sweep the problems or the measurements under the rug, because those often end up being very important clues for smart people. Likewise, I'm often asked, can we really believe an explanation without a hypothesis? That is, if somebody tells you what's going on, but they don't say how, right? Is that credible? And I think it's not. I think that is really the essence of science for us is, the present data that we have presents very formidable challenges. It's not easy. So when somebody just says, oh, it's new physics, or, oh, it's systematics, right? The problem is the data is so good now, you really need an explanation of how that can be so you can confront the data with that explanation. Otherwise, it's really not much more than somebody's gut feeling. And, the data is really too good for, going with gut feelings at this point. At this point, we really need explanations of exactly how to accomplish or explain the differences that we actually see. However, I think there are some really good reasons for optimism. There's new data coming in. I'm actually most excited about the Gaia Data 3, and that just came in a few hours ago. But there's LIGO, DESI, Roman, Rubin, Euclid, JWST, Simons, S4. Some of these will help characterize the expansion history recently that can help eliminate that as any possible part of this story. Some of the CMB experiments like Simons and S4 can look for predicted features from things like early dark energy or sterile neutrinos with some interactions. There could be completely different clues that are good for theorists, cosmic birefringence, tensions with sigma 8 or even BBN. I think it's always important to remind ourselves, there's a big playground out there still. Lambda CDM is the benchmark, but it is still 95% dark. And what underlies it is our missing theory of quantum gravity. So, there's no reason to be too shy about trying experiments now. And in fact, people are clearly voting with their feet and working harder on this problem. I've noted just recently, these are the number of papers per year just measuring the Hubble constant. And since this tension was first noticed, which I think was in the early 2010s, maybe 2012 or thereabouts, we've seen a factor of 10 increase in the number of papers. Some of them are good, even. One can't expect with a factor of 10 increase that they're all going to be right, but it's important to pay attention to that. Certainly, it demonstrates that the community is quite interested in this problem. So we're doing our best to improve the precision of our measurement. Later this year or the beginning of next, we expect to reach 43 Type 1a supernova calibrators from 3 more years of the Hubble Space Telescope. We hope to observe Cepheids in the Coma cluster as well. Over the next 2 iterations in this next year, I expect we should be able to get down to hopefully 1.2%. Stay tuned and keep looking at the other experiments that are going on in this field at the same time. So my final thoughts, I think the discrepancy is around 5 sigma. It could be as low as 4 or as high as 6. It really depends on which data combinations you combine, really. I think a simple way to say it is there really are no late universe measurements of good precision that are coming in lower than any early universe measurements. I think the difference appears robust. It requires, at this point, really multiple catastrophic failures to avoid. There's been no one systematic identified that can solve this without, as I said, multiple, that starts to become more conspiratorial. I think it's very interesting. Unless your Bayesian prior on vanilla lambda CDM is already very high, then it's something we should really be taking seriously. And I don't know why. I don't pretend to know the answer. I think we need to follow the evidence. I think we need to find the how. How is it that these things are different? I think it's an exciting thing to work on. And of course, always remember the universe might be more clever than we are now. So I will end there, and thank you for your patience and time.
Thank you very much, Adam, for this wonderful and so clear and precise lecture and updated of this crucial problem. And let us now to open the discussions, the questions, reactions, and as is you did precisely in the aim of this series of meeting, which is don't sweep the problems under the rug. And if the problem is today in the focus of cosmology, is in great part because of your work, but your perseverance to always put this in the way you explain it. You explain it here. With that said, so first question I see now is Christopher Tully, one of the lectures, has been one of the lectures in this school and from Princeton. So please, Christopher, activate your microphone and in a very precise way, address to Adam.
Okay, thank you. Thank you for
inviting
me on. Hi, Adam. I wanted to add, thank you, for immensely clear talk on the subject. I wanted to ask more of an instrumentation question.
Yeah.
As many of us have devices where we try to push for the ultimate limit that we can achieve. And it's regard to this, amazing ability you've gotten to the percent level of a pixel. And so I know you're measuring distances and using statistical averages to get down to that level. So since you're measuring, differences, you don't really care for a given star averaged over where it appears in a given pixel. So in some sense, if one just looked where they appear at the local coordinates in the pixel, one would expect, somewhat flat distribution. Does it cross-check that when you look at, the statistical power that you've achieved from the Hubble telescope, that the detailed of, I don't know if it's a CCD camera or whatever, it doesn't somehow skew, because your data set for the Cepheids, as you said, is going to increase with time, but it's not huge. So it's always one wonders about that.
So I think, are you asking about the calibration of, for example, the linearity of the telescope and how where how well we can make measurements over that range?
Yeah, at the sub-pixel range,
Okay.
when you're
Yeah,
at different reference points.
Oh, okay. So we're okay. I see where you're going. So I'll mention two different things, because there are two different issues here. One is when you're measuring the fluxes or the brightnesses of the stars, and you're using the same camera, making sure that you are doing that you are really getting a linear response of your detector over a fairly wide dynamic range. And I'm just looking here I have a slide, a backup slide on that. And so we do that by looking at sequences of stars that are calibrated with different kinds of detectors that are known to be very linear. And where is my slide for this?
Yeah, I understood the luminosity measurement. This is more, I guess what you would call the
So you're
parallax.
talking more about astrometry, I think.
Yeah,
so
that
was my other thing. Okay, yeah. So in that case, what we're doing is, you could. I'm looking for that in that slide. What we do is we centroid a star, right? And because we have a finite number of counts, right? We don't have an infinite number of counts. Then you cannot centroid that. Okay, here was the first slide that I was looking for. Sorry, I'll just show this briefly. This just shows the linearity of the scale. And so this is the true expectation, and this is what's measured from the camera. And this is done over 15 magnitudes. And it's done with various kinds of sources that are truth. But what you're asking about is astrometry and measuring to the sub-pixel level. So let me just get back to that part there. And so what happens when you try, here we go. What happens when you try to do that is you have this finite, you have a finite full well depth of your CCD. And so you can't collect photons forever. You hit saturation. And so what happens there as a result is knowing the shape of this point spread function. The point spread function is dictated by the optics of the telescope. So we know the shape very well. You could fit the centroid much better than a pixel. You could fit it to about 1/100th of a pixel. And then, as I described, if you drag the telescope, you can measure that over and over. Now, I think you were asking, what if the different pixels have different behavior?
Well, I'm just asking. So you have sort of a point spread function that's coming from the optics, but then you could have a sort of a non-uniformity, so that when you make these averages, that you don't actually land uniformly in the.
So that's actually what makes this technique more powerful than normal imaging, because see, in normal imaging on the left, you are sensitive to what if we try to map the pixels really well. That's what we do when we calibrate the Hubble Space Telescope. We use flat fields and the ratios of energy they see to essentially flatten them or match, correct their geometry to all be the same. Nevertheless, there could be tiny errors there. And so when you observe a star at a given location, you have those tiny errors affecting it. By moving the star over thousands of pixels, we're not only getting higher precision, we're actually averaging over those systematics as well. Because, if each individual pixel has a slightly different size than even after calibration than you thought it did, then you're averaging over thousands of those.
Okay, so I guess I can see that the point spread, it looks like it must be over like 5 or 10 pixels. So I guess you're.
Oh, yeah. And sort of the proof in the pudding, I guess I would say, is if you just look at the fluctuations that you see star to star, and if you assume that it's solid body motion of the telescope causing the stars to bounce a little in the direction perpendicular to the scan, you can see that we're really measuring that in a very similar way for stars that are landing on different pixels, such that when you subtract them, you get a much smoother, simple noise looking result. And so that is a consequence of what you're describing as well. The fact that, if you had tiny errors or differences between pixels, that you're reducing that. Also, to mention, this is only now one of 7 different ways, independent ways, that we use to calibrate the Hubble constant, right? There's parallaxes that are measured from Gaia, which uses a totally different technique. There's parallaxes that are measured from the fine guidance sensor on the Hubble Space Telescope, which uses it's a white light interferometer. So that's still a different technique. And then, of course, there's the detached eclipsing binaries in the LMC and the masers in 4258. So
okay, I didn't appreciate that. There's all of these cross checks. Thank you for explaining that.
Sure.
Thank you, Chris, and thank you, Adam. And so next question is by Bozena. So please address your question or points to Adam.
I had a question about eventual role of preselection of your supernovae. Do you have to do any special preselection of the sources? And if so, would that be a kind of a bias present in the considerations, or you think this is not a problem?
Right. That's a good question. So in general, the one selection that sort of everybody uses for type 1a supernovae is what they call quality cuts. And quality cuts really means using the highest quality data. That generally involves the objects that were sampled the best. So sometimes a supernova is not discovered till after maximum light, and then you miss a lot of information. Or you sometimes have supernovae that have extreme colors, implying, there may be a great deal of dust around it. And, generally those kinds of objects are going to give lower precision. And so there are quality cuts that are defined when people do cosmology. And, I would say in terms of the supernova, probably 95% of supernovae pass those. In terms of how well the data has been collected, probably 80% pass. And so those quality cuts are used both for the distant ones and then the nearby ones in the Cepheid host. We use those same quality cuts. And as I said, by the end of this year, we will have finished a complete sample. We will have measured every type 1a supernova in the last 40 years that passes the quality cuts. So it's kind of a 40-year sample. And so then there's no selection other than passing those same quality cuts.
So nothing is done by hand in this sense.
No.
Should be objective. Okay, thank you.
Thank you. So next a question or comment is by Bill Green from Florida, Tallahassee. Please, Bill.
Yes, thank you, Norma. That was a great talk, Adam. You may have mentioned this, but how tightly have you been able to constrain the evolution of type 1a luminosity as a function of redshift or age of the universe?
Right, that's a great question. I would say detailed studies of them have shown, here I'm gonna get picky with words and definition of what we call evolution versus what we call demographics. And so we already know that there is a range of type 1a supernovae, from the ones that have broader light curves and are more luminous, and the ones that have narrow light curves and are less luminous. And that is already used to standardize type 1a supernovae. When we look back at higher redshifts, we do see the demographics change. We see more of the broad light curve ones and less of the narrower ones. That doesn't produce evolution because, as I said, we correct for that. Evolution would be to say that at a fixed light curve shape, that the luminosity is still different somehow. Right. And nobody has found evidence of that yet. It's hard to see, but basically we look at spectroscopy in detail. We look for the type 1a supernovae to look different, and we really haven't seen evidence of that. We go to very high redshifts, up to redshift 2 even, with type 1a supernovae, and they seem to continue to follow this sort of standard model. You would expect if there was evolution that it would grow with look back time. It would grow with redshift so that, eventually you would break them. You would break the type 1a supernovae at redshift, 2, 3, something. And that hasn't been seen yet. All the measurements I've been talking about measuring H0 are all done at extremely low redshift, at redshift 0.04 and 0.05 is sort of the mean. And so, evolution isn't even part of the story here. You're talking about look back times of just a couple 100 million years. But we are certainly paying close attention for that at high redshift. It's, one of the reasons we compare high redshift type 1a supernovae to baryon acoustic oscillations. And right now they're both arguing for W being close to -1. It would be pretty amazing if you had evolution that was changing the type 1a supernovae in just such a way as to bring the equation of state to look like -1. So it's really evolution plus not -1, leads to looking like -1 fortuitously. And now it's been measured to about, 5%. So, I guess I would say overall, we've looked, we have ways to look. There's been no evidence of it. There are certainly demographics changes, but no evidence yet of evolution.
Or evolution of local environmental conditions over time that might affect luminosity.
Correct.
Thank you.
Thank you, Bill and Adam. And so next question is by Anthony Lasenby from Cambridge, UK. So please, Adam, Anthony, ask to Adam, please.
Hi, Adam. Thanks very much for the talk. So I just wanted to ask about the tip of the red giant branch results. They do seem to look as though they're systematically lower in terms of H0 than what you get from the supernovae. Do you believe there is a systematic difference there? And if so, what is it due to?
Yes. Let me, my preference would be to pull, let me pull this up. So this is sort of the latest compilation, I would say. And what you're talking about is the group of blue points here.
Yeah.
Okay, yeah. So these are using TRGB and type 1a supernovae. So I could say a couple of things about these. I mean, one is, if the hypothesis is that the late universe and early universe are giving different values, unfortunately, the TRGB results don't really tell you whether that is true or not. They are really consistent with either. That's partly because they have larger error bars. That's partly because their values are a little bit lower. So, that's just the simple statement. I mean, I don't think it would be reasonable to say, oh, if I only choose the tip of the red giant branch and I ignore, Cepheids, Miras, Mazars, Tully Fisher, surface brightness fluctuations, type 2 supernovae, maybe I can get out of this. In order to go there, you would need to have a story, of why that would be the case. Okay. So I would say, to first order, there's no reason to have an explanation because these blue points are consistent at sort of 1 to 1.5 sigma with, this sort of fat blue line or the set of other measurements. However, having said that, what do I think is going on? We've begun looking closely at the TRGB results. And, there's two things I can tell you right up front, which is I think that there is, at least I have some reasons to believe that the luminosity of TRGB, the calibration, might not be exactly the same that some groups have used. I think this shows up in this paper, which I'm a co-author of, Juan et al., 2019. You see this data point here. One of the tricky things about calibrating TRGB, unfortunately, is you have to estimate how much dust is in the Milky Way, how much dust is in the Large Magellanic Cloud. Now, I've spent a lot of time talking about dust. We make our measurements in the near infrared to avoid dust. And we make our measurements differentially. TRGB doesn't work that way. It's in the optical and it's not differential. And so therefore you have to estimate the dust in the LMC. And there's a lot of debate about how much dust there is. I think a more reasonable estimate for the LMC dust that's done independently would give you something more like this blue point, not wildly different than this blue point, but it is closer. Another point I would make is some of the more distant TRGB measurements that have been made don't look robust to me. Hopefully I could say more about that later. But TRGB is much fainter than Cepheids, and you get to a distance where you just can't see the break anymore. And we have looked at some of the more distant galaxies where TRGB has been measured, and we don't see the break. So these are just at the sort of hairy edge of where you may or may not even be able to do this. So I think it's interesting. I certainly am looking forward to Gaia DR3, hopefully can finally calibrate TRGB. I mentioned that as well. TRGB has never been calibrated with parallax measurements, let alone with Gaia. And so, you know, if the Gaia measurements are as good as they're starting to look, we might resolve that as well. So certainly it's something to keep an eye on. But as I said, to first order, you know, there is nothing inconsistent between TRGB and actually either set of measurements because of the size of the error bars. But from things I've looked at, I think that Cepheids and TRGB are much more consistent even than you're seeing here. It just has to do with using consistent calibration between them.
Okay, thanks.
Thanks very much, Anthony and Adam. So, are there more questions, comments, reactions from the audience? George Smoot, please, George.
All right, thank you. I was hesitating because I first want to tell Adam it was a great talk. And second of all, I want to cause trouble, but I want my relationship with you to still be good.
Okay.
So take it in the
respect you in the morning.
I fought decades ago an unsuccessful fight to convince people not to call it the Hubble constant, but to call it the Hubble expansion rate.
Yes.
Now you just on your screen.
You lost.
Yes, I lost badly.
Yeah.
On your screen, you're also just showing a Hubble expansion rate. You should set a Hubble constant that is projected at the present time.
Right.
But what if you show this plot as a function of the Hubble expansion rate versus redshift, and then put the data points on it? You will see automatically it takes either a certain kind of calibration error or a certain kind of physics. A lot of the physics things that people have brought up just don't make sense when you realize what you have to do in order to do it. So when you're looking at those points that are coming from the baryon acoustic oscillations, they're at a redshift of 0.5, right? There are some others that are further back at a redshift of 1 and 2. And then there's the CMB, which is actually a prediction that extends down from a very great redshift. And you expect this kind of U-shaped curve, except it's very lopsided. I could do, if you let me share my screen, I would do that.
Yeah, if you give me a second, I'm gonna.
If you have it, it's better, because I don't happen to have on my hand the one that I wanted to, which was the most recent data, which I've seen.
This is the kind of thing you're looking for,
right? But with the data points on it.
Yeah. Hold on. Now I'm going to find it with the data. I have that one as well. Let me see if I can find that in a second here. You know, you don't always have all the backup slides. I usually, believe it or not, that's the one I usually show more for like my public talk.
Okay. Well, it's the one where the physicists or the astronomers should be looking at it, because they realize there has to be something that happens between a redshift 0.5 and 0 in order to explain this discrepancy.
Yes.
Right? Or you have to shift the whole curves, everything at redshift at 0.5 and greater, you have to shift them up.
Right. I agree with you 100%. You're definitely not creating a fight.
I didn't want to offend you, because your talk was great. Your explanation was really good.
No. You're right that it's a simpler way to think of it for a lot of people. And I'm going to find this here. Hold on. I may have just found it. Yes, I think I found it. I think you'll like this one more, at least. Let me stop sharing that screen and start sharing a different screen.
Yes.
Let's see if you like this one more. Okay, can you see that?
Yes.
Okay, so this is sort of what George is saying is, look, we have a very precise measurement here. We have a shape thing here. You get to play with that shape thing a little bit. We've got some crude but reasonable measurements of high redshift supernovae here in red and baryon acoustic oscillations. And then we have a very tight constraint. You could sort of see it as a value back here. And so, you know, that's why it's tricky. So George, just to say, when people talk about a late time solution, they're really talking all the way back to recombination. They're talking about anything they do with the shape of this curve. And that's sort of H of Z after recombination. When we talk about an early solution, we're really talking about changing the calibration of the CMB itself. So that wouldn't show up on this curve. It would be like changing the sound horizon, or, you know, where the Doppler peak would occur. Right. So it's not this part of it.
you either have to change the model or
Yeah.
you have to shift the curve up and down, right? In
Right.
your plot, you've shown the curve going right through your data point.
Right.
Whereas usually in the plots that everyone else makes, your
Right, it just
your
depends
data
where
point
you
is
want-
above the curve, right?
Yeah, because it just depends whether you set the curve here and then run it backwards, or I mean, we don't have to call this the Hubble constant tension. We could call it the sound horizon tension, because
Yes.
Right.
start with the Hubble constant. You could get, your lambda CDM parameters from, high redshift supernovae BAO to do H of Z. You go all the way back to the CMB and you predict the sound horizon, and it would disagree there.
Right. Now your red points are the supernova points. Are they the baryon acoustic oscillations are the red points, and
Or the baryon acoustic oscillation points are the green points.
the green points? Okay.
Yeah.
So that makes sense because they're green on the right. Yeah.
Yeah.
So what you're saying is somehow you have to either shift the shape of the curve or you have to shift the whole curve up and down.
Right. That's right. And so the easiest way to play the game was just to make this curve, this dark energy dominated part, steeper, because when you do that, everything works. You don't see it in the form, you see it in the form you're thinking of.
Right.
I might have, I may still have another version that you like even more. But the point is that you can't do that because those darn supernovae get in the way, the supernovae and the baryon acoustic oscillations.
Yeah, your curve is better, but you projected it to the present value in that curve.
Yeah.
Whereas it's got to have 1 plus Z factors in it.
Right. I wasn't totally ready for you, George, but here, I'm going to try one more time.
Well, I wasn't meaning to give you a hard time. It's just that,
this is great. I'm always learning which backup slides to have. Let's see. Well, okay. You want something like this still. I'll try one more time, but unfortunately the data is going to kind of go away. Screen share. This is the curve. This is what they show a lot for W first these days.
Okay. What I have is one that we show off for Daisy.
Right. But so can you see this slide?
Yes.
So George,
Now, I don't see the data points, but
wait, sorry. Do you see the W first slide?
yeah.
Yeah.
Okay. So this curve is set following Planck. Okay. And so that's why you see the curve end at 0 and it's like 60, whatever, 68 here. So, imagine a data point up here. Right. And so you go, oh, you're just not fitting there. Why don't I just make this curve steeper? This dark energy thing steeper, and I'll reach it. And the answer is that would be W less than -1. And if you stuck the supernovae and BAO on here, you would see that that isn't really a good option because you're going to start to violate that data.
But I mean, you see a lot of papers out where people are trying this kind of modification or addition to the standard model that just don't have a prayer of making the curve have the right shape.
Right. But so I would say you can't make that curve any shape you want. There's too much data. And so that's a problem. And that's why people have gone to changing the model at early times. See, when you stick I'm just as an example, if you stick a neutrino in the universe, it doesn't change the shape of this curve at all because the universe is so, neutrinos are so subdominant after recombination. But it does change things in the early universe, like it changes the amount of energy in radiation-like material, which changes H of Z at early times before recombination, which makes the universe become transparent earlier. And that wouldn't affect the shape of this curve at all.
Yeah.
So, yeah, I understand that. I just think it's a disservice to some of the people who are looking at this to talk about the Hubble constant and just having it one-dimensionally shown when it's clearly
it's
a
a
dynamical
disconnect.
problem.
I mean, that's why I really like to call it an end-to-end test. It's a disconnect from one end to the other. And, you say, I have a disconnect between two ends and I have a shape that has to be pretty close to right. And it's not connecting these two. So the two solutions are to change the shape, but that's, will violate other data. Or, as I said, this calibrate, I would, like a calibration change in the early universe that is also changing the model. It's just changing it before that shape becomes relevant. So
Right. So I can agree with that. It has to do, either you have to have some, that 0.2 magnitude error somewhere, which is difficult to believe, or you have to do some renormalization. Changing the shape of that curve requires you to do to things that are too hard to do to general relativity or anything else.
Right.
Well, thank you. Sorry, thank you, George, and thank you, Adam. Are there more? Do you want to add something, Adam, to what George said at the end? If not, we proceed.
No, I think we're in total agreement.
I will comment on that. Yes, thank you. And are there more questions, comments, reactions? Is the time to do so from the audience? I don't see any more hands. So I would like to thank, of course, you, but before of that, I completely agree that the problem, what is said, the Hubble constant problem, which still today there are many teams or many places in which there are no acknowledge of the problem. They just said, let us do. It's a question of systematics. Semi-B is very precise measurement, etc., which I do not agree. I completely agree with your presentation, I mean, from the beginning. And in fact, in this school, from the first release, and there are many people here who can also support that, from the first release of Planck, in which the release was with a very the low Hubble constant, we put it in the session, and I mean, and 2013, we put this problem, and we address it, and it will be a big discussion because many people were there to discuss, and we propose it as one of the solutions to reanalyze or to the early universe data. I mean, reanalyze the Planck data, because at the time there were not other data. It was the first release. And because there were the problem of so-called effective degrees of freedoms, I mean the neutrinos, which go in the direction of, if you put that, if you do a more complete analysis of that, that make right. Just a moment, please. And then it was then after that this do not make the case. I mean, all these different type of adjustment by changing some parameters of the curvature, the spatial curvature, it was a proposal. None of them do the case. None of them do solve in some sense the problem. So this is a real mismatch between the early measurements, because besides Planck, there are the ACT, I mean, the Atacama cosmology.
That's what I wanted to add is, just to be clear, I have no reason to doubt the Planck measurements. There have been great measurements from ACT, from WMAP combined with BAO, and they seem very consistent. And so
of course,
it's not, I don't want to imply that there's any problem that I'm aware of with Planck. I think it looks very good. And I also recognize that the simplest answers, making W less than -1, just adding a neutrino, or, aren't quite simply the answer either. Maybe some more complex versions, neutrinos that have the right kind of interactions, that they don't damage the CMB,
Yes.
or early dark energy. So, or none of the above. I mean, I don't know. I don't know.
I completely agree. I mean, and all the others said early type measurements give, or other CMB teams said there are recent, give this law an agreement with Planck, said. So there is really a mismatch between the early, between what is measurement at the early, the sound horizon, and what is measurement in the late universe. I think the way is not change the best pillars of the model, which are general relativity, which is very well measurement in the late measurements of the strong gravity or so on, is the way in which we understand the early universe, and the sound, and that plays the role, the full role of dark energy, early dark energy, and the way in which the sound horizon could be decreased.
Just to sort of close this out, I guess what I would say maybe to George, but more broadly, is we cannot get the sound horizon to square with the Hubble constant.
No.
And that's probably the simplest way to say it. We thought we could get them to square with the cosmological model, but really good measurements of the sound horizon and of the Hubble constant don't get squared. You can't go from one to the other using the cosmological model, and we don't know why.
But one possibility is that really, and that also could come with more measurements of the Hubble growth. The growth. We need really to have good measurements and more expanding redshift for that. And then one of the ingredients to understand is the dark energy, because dark energy could play a role in the early universe, and that is an open problem. We know inflation is dark energy in the sense of vacuum energy. And vacuum energy is more general than just a cosmological constant. And all the late measurements are in agreement with, are compatible with a cosmological constant. A cosmological constant is also vacuum energy. And there is no reason that this vacuum energy could be everywhere the same from the early to the late universe. We know the vacuum in physics is the more important ingredient. We live in an empty universe in some sense, and the classical vacuum, the great voids measurement by the astronomers, is filled by the classical cosmological constant in some sense. But the early universe, there is also vacuum. In fact, inflation is driven by the vacuum, the quantum fluctuations of the vacuum, and so this connection could be very important to understand.
Sure, Norma. I think this is probably a good point to end the Zoom webinar or meeting. We've gone on a while, but I want to thank you very much and thank everybody for joining. And it was a very enjoyable 2 hours.
Yes, thank you very much. Thank you very much to you, Adam, and thank you very much to all participants. And I hear participants from many places. If you allow me a second more, I would like to mention that we have here also Dr. Alba Zanini from the ENFN of Italy, and President and Ambassador of the city of Turin for scientific culture. She's physicist, of course, Ambassador of our school in Italy, and President of the chorus Association for Scientific Culture and Culture. And this was very followed in Italy too. And so with that, I see here now many of the participants who are for some while I didn't so I want to thank. And to say that in the tradition of the school, it was champagne, and you know that I am offering champagne to you, and always with the medal, the true French champagne, one of the, and this is for always to the medal and the wishes to get a Nobel Prize. So that is why I said to you, we wish you another Nobel Prize. And this is for all participants. We share the champagne.
Thank you. Thank you very much. And I hope to see you all in Paris next year.
This is for you. This is for when you come to Paris.
Yes. Don't send that to the mail. Yes. All right. Thank you. Take care.
So thank you very much.
Bye.
And bye-bye. And
Bye-bye.
we see next year.